I hope everyone's doing well. I am Mr. Ish. We're looking here at a good example, a variety with regards to length of a spiral. Now, if you think about a length of an arc, we know there's a certain formula, and I'll put it for you here. And you're familiar with this formula, which is involved for determining a length of an arc. You have a lower limit, a to b, upper limit, and integral. And then here you know you have a 1 plus a dy or dx. This right here is your derivative coming through, obviously dx. When you're looking at a length of a spiral which involves polar coordinates and you're looking here at polar curves, this formula is slightly changed. And what is it changed to? I'll show it to you. You're looking here at a length of a certain arc arising from a polar curve from a lower limit to an upper limit. But these limits here, A, would be represented in terms of radians. Theta 1, theta 2, theta 1, theta 2 coming into play. Then we will again have this. But here we'll have a certain other symbol, a Greek alphabet symbol, lowercase, which is to be rho. That's what we have, RHO, and it represents that lowercase slant p squared plus a certain derivative with respect to that squared. Here we have this symbol coming again with respect to the theta variable, all squared, and we're looking at everything with regards to the angle d theta in radians. Look how this has changed a little bit. We have lower limit, upper limit in respect to radians. We have that squared plus that derivative squared, all in the square root, and everything with regards to your theta variable. This is the formula we'll use to determine the length of a spiral. What will our spiral be? Our equation here for a certain polar curve will be this. That symbol coming again, we'll call it rho. Rho is equal to what? E to the power of 2 theta. It's an example of a polar curve which is a spiral. If you were to graph it out, I'll show it to you momentarily. We can determine the arc length, the length of that spiral. And we will be looking here from a 0 radian to a 2 pi radian. And I'll show you what it looks like, but that's what we are determining the length of a spiral of. So that's what our polar curve is, e exponent 2 theta from 0 to 2 pi. If you were to look at the spiral, you're originating from over here and then it's going here. This is 0 and then coming back to 2 pi, you end up right over here. This right here is our spiral, e exponent 2 theta from 0 to 2 pi. That's what it looks like. We're determining the length of this curve or arc. You can call it length of an arc. It is an arc to a certain degree, but it is more of a spiral. And that's what we're determining, length of this spiral. And we'll look at it by means of this. But look, when we're looking at this equation, we're seeing a couple of items come through. We have to determine them. This right here is my theta 1. This here is my theta 2. So we have our limits already determined. Now what we are looking at is this. Rho squared plus derivative with respect to the rho and your theta variable whole squared within a root. And how do we determine these? Well, do algebra. You know rho is equal to e exponent 2 theta, which is your equation of your polar curve. What's rho squared? And you're going to run this through algebra. You have e exponent 2 theta squared, which you know to be e exponent 4 theta. What's derivative of this? Because now you have to do the derivative. If rho is equal to e exponent 2 theta, what's the derivative? You are basically using your easy template for a exponential derivative function. You will have your 2 e exponent 2 theta. But then we're looking here at the squared. When we square it, which is what's going to come into our formula, what do we have? 4e exponent 4 theta. That's what we have. Now let's bring everything here to this integral. I have a lower limit a, which we now know to be 0. I have an upper limit 2 pi in radians. I have a rho squared, which here is e exponent 4 theta. Let's put that in, e exponent 4 theta. I have this, it's already determined, 4e exponent 4 theta. When I do it, I bring it in, 4e exponent 4 theta. But these are common terms because they have a common base e. Everything adds. I have a 1 plus a 4, which is a 5e exponent 4 theta. When I combine these by means of simple arithmetic, I am really looking at 5e exponent 4 theta. Now, if I use laws of radicals, I can separate these into their individual radicals, and there's nothing wrong with me doing that. I have a 5 over here. Then I'll break this away and I'll bring this into its own radical. I can push this root 5 out, it's a constant. I have here a root 5. Then I'm looking at a lower limit, upper limit, then I have this e exponent 4 theta in a root. You can easily determine that. You're going to do the square root of this exponent. You'll have e exponent 2 theta d theta, and this right here becomes our integral, which we have to solve, and it's easy. You're thinking back to your basic integral formulas where you are having here a exponential. e to the power of ax, when you're doing its antiderivative, you're doing a 1 over a e exponent ax. That's what I have. That's the antiderivative. You're going to bring everything into that same form. I have here a 2 which is an a. When I do it, I'll have a 1 or 2 come out. I'm looking at root 5 over 2. This 2 is coming from right here using the template. Then I have e exponent 2 theta. I'm looking here at upper limit 2 pi and a lower limit 0, and that's what we have to do, and we are so close to being done. You put the upper limit, lower limit, the difference of the two. I will have here my spiral length s is equal to root 5 over 2. I'll have e exponent 2 theta, where the 2 pi is coming in, will become a e exponent 4 pi. E exponent 4 pi minus 0 coming in here. E to the power of 0 is a 1. This right here is our answer. Root 5 over 2 parentheses e exponent 4 pi minus 1. If you compute that, you'll have the length of this spiral for this specific polar curve from 0 to 2 pi. You've done a single turn of a spiral, but because it's a spiral, these two ends don't coincide. You have a spiral effect because it's gonna continue like this, like a spiral, and you can change that upper limit as you want to determine the length of the spiral. If you change this to the number of turns you're interested in, you can easily run everything down through this same integral, same formula and everything. You'll get your new value for that new length of spiral. What's your units for this? Whatever they might be. Root 5 over 2 e exponent 4 pi minus 1 units. That's the length of this spiral that you see over here in the solid representation. Thank you for watching. Have a good day.